Let's consider the chapter of current electricity. Talking about current electricity, one should know what exactly is current, how current is constituted, what makes up for current. So when we talk about current electricity, we should know certain parameters and certain characteristics of what exactly electricity is all about. Definitely it is one form of energy which is a part and parcel of physics. So today we are going to consider how we are going to go about with current electricity. As far as the basics that are concerned, that is prerequisites. Talking about prerequisites, we should know certain terms. What is potential at a point? What is potential difference? What is current? What is resistance? What is resistivity? What is conductance? And what is conductivity? Based on these, we go on for what we call as a universal law, which is Ohm's law. With Ohm's law, we have resistances that are connected in series, resistances that are connected in parallel. We have a few conclusions that we derive as far as this particular sector is concerned. And then, of course, let's not forget the most important part in this chapter, that is the numericals. This chapter has more weightage towards the numericals. So the inclination is more towards the numericals rather than the theory. However, we do need to know what the theory is all about, because then and then only it is possible for us to go ahead with the numericals. So talking about certain concepts, as I said, first and foremost, we should know what is potential at a point. Potential at a point is defined as work done in bringing a unit positive charge from infinity to a point. Where is this point? This is a point in the vicinity of the electric field. What is this concept of vicinity of an electric field? If I have a static charge of 1 coulomb and we are considering the space that is surrounding it, we say that the place or the space surrounding a charge wherein we can experience the presence of charge is called as vicinity of the electric field. So if I have to consider the potential at that point, which is placed in the vicinity of an electric charge, we say potential at that point is defined as work done in bringing a unit positive charge from infinity to a point in the vicinity of the electric field is called potential at that point. The SI unit of potential is volt. As we have potential at one point, we also can have potential at a corresponding second point. So we are selecting another point in the same vicinity. Definitely the work done is going to be different. So we say that work done in bringing unit positive charge from infinity to another point in the vicinity of the same field is called as potential at that point. Both the work dones are different, so potentials are different, and the difference in the two potentials is called as potential drop or potential difference. Now that I have the potential drop, definitely I know that there is a flow of electric charge. This electric charge is flowing through a uniform cross section of a conductor in unit time. So the rate of flow of electric charge per unit time is defined as current. SI unit is coulomb per second, that is ampere. So I define 1 ampere current as 1 ampere current is that current which flows through a uniform cross section of a conductor when 1 coulomb charge flows through it for 1 second. Mathematically, 1 ampere is equal to 1 coulomb upon 1 second. 1 ampere is equal to 1 coulomb upon 1 second. Going on to the next one, that is, when I say charge is flowing through it, I have a potential difference. I also have certain opposition that is exerted by the conductor on the particular flow of charge. So when I talk about the resistance that is offered or the opposition that is offered to the flow of electric charge, we say that this particular parameter is the resistance of the conductor. So I define the resistance of the conductor as the opposition to the flow of electric charge per unit cross section of a conductor in unit time is called as resistance. So resistance is nothing but the opposition. It's similar or analogous to your frictional force that we have in our day-to-day life. But this is concerning your electricity. So it's flow of charge basically. Opposition to flow of charge is resistance. The property by virtue of which resistance is offered by a conductor is called as resistivity. Resistance, resistivity. Similarly, the opposition is the obstruction that is there. Opposite to it, we have something what is known as conductance. So the ease with which a charge flows through a conductor is called as conductance. It is definitely opposite to that of resistance or reciprocal of resistance. SI unit of resistance is ohm. SI unit of conductance is ohm written in the reverse order. That is M, H and O. As we had resistance, resistivity, we have conductance and conductivity. In case of conductivity, it is the property by virtue of which the charges can easily flow through a conductor is called as conductivity or conductance. After knowing what is conductance, what is conductivity, resistance, resistivity, potential, current, after knowing all this, we go on to a universal law which is known as the Ohm's law. This is always a question based on Ohm's law, wherein they say state the Ohm's law. To understand it, see, I don't want any one of you to really go about with learning things by heart. So how do we understand it? Let's consider a conductor. Potential drop between the conductor is given as one end of it is say 10 volt. The second end is 6 volt. What is the drop in potential between the two terminals? 10 minus 6, that is 4 volt. Supposing I change that 6 volts to 4 volts. So what is the drop between the two ends? 10 minus 4, that is 6 volts. Let's consider another example. The second end has a potential drop as 2. So 10 minus 2, that is 8 volts. Now I have three different cases wherein I see that there is a change in potential. So we say that greater the potential drop, more is the current that flows through it. That means current flowing through a conductor is directly proportional to the rate of change of potential between the two ends of the conductor. So if I have to state it in a statement form for Ohm's law, we say physical conditions of a conductor remaining constant, physical conditions like temperature and pressure, current flowing through a conductor is directly proportional to the potential difference between the two ends of the conductor. Mathematically, V is proportional to I. If I remove the proportionality constant, I use V is equal to I multiplied by R, where R is the constant called the resistance of the conductor. This is as far as mathematical approach is concerned. We prove this Ohm's law even graphically. That is, if I plot a graph of V versus I, V along the y-axis, voltage along the y-axis, and current along the x-axis. I see the nature of the graph is a straight line. How do we interpret straight line graph? You must have studied in your 9th standard. Interpretation of a graph. A straight line graph indicates that the slope of the particular variation is constant. So I know that the variation of voltage against current is constant. That slope in this case is change in voltage upon change in current. Change in y coordinates upon change in x coordinates. So I get change in voltage upon change in current, which I say is a constant. That is nothing but the resistance of the conductor. So if I cross multiply, I get change in V is equal to current multiplied by resistance, which is nothing but the statement of Ohm's law. So I can prove Ohm's law graphically also. On proving this, I say that the substances which obey the Ohm's law are called as ohmic conductors. And the substances on the reciprocal side, the substances which do not obey the Ohm's law are called as non-ohmic conductors. What about the non-ohmic conductors? If I plot a graph again of V versus I get a characteristic curve which is similar to your Ogive curve in statistics. It's an elongated S, meaning thereby if I have to take the slope at any point, I draw a tangent to that particular curve. I see that the slope of the tangent is varying across the particular graph, and hence slope is not equal to a constant. When slope is not equal to a constant, I definitely can say the variation of V versus I is not constant. And such conductors which do not obey the Ohm's law are called as non-ohmic conductors. Ohmic conductors, metals, all conductors are ohmic conductors. Whereas as far as non-metals are concerned, or semiconductors like diode, triode, pentode are all examples of non-ohmic conductors. Then after having this base of your electricity, we go on to the combination of resistances. In day-to-day life, we see that we use resistances in combination. So we have resistances combined in two ways. One is resistance in series, the other is resistance in parallel. If I take resistance in series, what exactly do we mean by resistance in series? Say I'm a layman in physics, I don't know anything about physics. How do I decide whether resistance is connected in series or resistance is connected in parallel? The place where current enters the resistance, the current enters the resistance is called the head of the resistance. And the place where the current leaves the resistance is the tail of the connector. So when the current flows through the resistance, we say that when head of one resistance is connected to the tail of the other, when the head of one is connected to the tail of the other, resistances are said to be connected in series. However, I said this is a layman definition. The one who doesn't know anything about physics will give such type of a definition. However, we have to connect this particular resistance combination into a circuit, into an electrical circuit. That means I have to connect such two resistances with the help of a battery source. When I connect it with the battery source, definitely current is going to flow through it. When current flows through a series circuit, the current is constant throughout the circuit. So first conclusion as far as series circuit is concerned, The current flowing through a series circuit is constant throughout the circuit. Second one, since I'm applying a battery source over there, it will definitely have a potential drop or a potential difference. This potential drop that is applied by the battery is equal to sum total of individual potential drops across individual resistances. So if I have resistance R1 and resistance R2, the corresponding potential drops are V1 and V2 respectively. That becomes my second conclusion as far as series is concerned. To obtain the third one, what I do is that I have the relation V is equal to V1 plus V2. If I apply Ohm's law, I said Ohm's law is always at your rescue as far as current electricity is concerned. We apply Ohm's law to this particular relation. V is equal to V1 plus V2. If we apply it, we get IR is equal to IR1 plus IR2. IR is equal to IR1 plus IR2. On the right hand side, I can take I common. If I take I common, I get I into bracket R1 plus R2. Now since I know that I is not equal to 0, the current flowing through this combination is not equal to 0. Hence, this I can divide on both sides. Dividing both sides by I get R equivalent is equal to R1 plus R2. So the combination of resistances connected in series is the sum total of individual resistances. That becomes the third conclusion as far as series is concerned. So just to take a recap of what we did here as far as series is concerned. First conclusion, current is constant. Second conclusion, V is equal to V1 plus V2. That is, the total potential drop applied is equal to sum total of individual potential drops applied across individual resistances. Third one, R equivalent is equal to R1 plus R2. Sounds very simple, but then when we go in for numericals, we ought to apply all these three principles if it is a series circuit. So in order to identify whether a particular circuit or a combination is series or parallel, we ought to apply this rule whether the same current is flowing through it or not. If the same current is flowing through it, definitely the combination has to be in series. Coming down to the second combination, that is resistances connected in parallel. When we have resistances connected in parallel, as I said, we have a layman definition. The layman definition is again related with the head and tail. So when the head of one is connected to the head of the other, that means both the heads are connected together, or when the tail of one is connected to the tail of the other, we say resistances are connected in parallel. Again, a very premature definition of resistances in parallel. However, on technical grounds, if we have to define the same combination, we go ahead as we are connecting both the resistances R1 and R2 with the help of a battery source. Now this battery source is going to allow current to flow through it. Remember, the potential drop across the battery is V. Current flowing from the battery is I. Let's trace the path of a current. I has started from the positive terminal, has started flowing through the circuit till it reaches the junction node A. You remember junction, when we talk about even railways, it's a junction, railway, Kalyan junction. Why do we say it's a junction? Because that is the place where we have a split of path. We have two ways that we can go across further. That is why it's called a junction. Similarly, here also we see that when current is flowing from the positive terminal till it reaches junction A, there is a split in path. That means the current gets split up into two paths, I1 and I2. This is with regards with the resistances that are connected there. So whatever current is going to flow through R1 will be proportional to the value of R1. Whatever current is going to flow through R2 will be proportional to the value of R2. Keeping this in mind, so I know I is equal to I1 plus I2. So this becomes the second conclusion. Again, I is nothing but current, that is electrical energy. We know that energy can neither be created nor be destroyed. It only can be transformed from one form to another. In this case, I know that I is getting split up into I1 plus I2 without loss of energy. So that is the second conclusion. In order to get the third conclusion, which law are we going to use? Yes, it is the Ohm's law that always comes to your rescue. So if we apply Ohm's law over here, we get I is equal to I1 plus I2. So instead of I can write V upon R. Instead of I1, I can write V upon R1. And instead of I2, I can write V upon R2. So I get the relation as V upon R is equal to V upon R1 plus V upon R2. From the right hand side, I can take V common. If I take V common, I get V into bracket 1 upon R1 plus 1 upon R2. Now since V is not equal to 0, I can divide both sides by V, thereby getting the relation 1 upon R is equal to 1 upon R1 plus 1 upon R2. If I take the LCM and reciprocal, I get the equation as R equivalent is equal to R1 R2 upon R1 plus R2. If I have three resistances that are connected in parallel, what should be the equation? I want it in the simplified form. Yes, indeed it will be 1 upon R is equal to 1 upon R1 plus 1 upon R2 plus 1 upon R3. But if I take the LCM and reciprocal, what should it result in, or what should it sound as? It works out to be R equivalent is equal to R1, R2, R3 divided by R1, R2 plus R2, R3 plus R3, R1. With this, we see that we have resistances connected in series, resistances connected in parallel. These are always going to be handy when you're going to solve numericals that are based on this.